when I applied for my job here at UWM, I've been here since 1990. So it was my 35th year. But when I applied for my job in 1989, I had never heard of UWM before, except for one thing, and that was this person named Robert Greenler, who maybe you have heard of. He was a longtime physics professor here at UWM. He retired maybe 10 years ago or so, and he was and still is the world's leading expert on rainbows and other forms of atmospheric optics. And I knew about him because he was one of my heroes, and I had read the books that he had written. And when this job opened up, and I thought, oh, I've heard of UWM. That's where Robert Greenler is. So I've always had this affinity for atmospheric optics, and I got to work at the place where the superstar worked. So that was kind of cool for me. Anyways, here we go. So atmospheric optics obviously involves the interaction of light with the atmosphere. So let's start by talking about some basic properties of light. So when light passes through the air, four possible things can happen. So one of those things is called transmission. That's when light passes through a medium, and in this case, the medium is the air, and the medium has no effect on it at all. An example of that would be light passing through a window. As you know, glass is the material that's used for windows, and that's because glass has excellent transmission properties. It allows light to pass through it without affecting it at all. Light doesn't heat up the window, the glass. It's not reflected by the window, it's transmitted. Okay, so that's one thing that can happen. Another thing that can happen when light passes through the air is it can be absorbed. Now, air is a very poor absorber of light. It usually doesn't absorb light at all. But when there are things in the air, the light can be absorbed. Things like raindrops, cloud drops, pollution. Now, when light is absorbed, the energy from the sun is transferred to the object that does the absorbing. So for example, if you were to lie on the beach, soaking up the rays, then, your skin gets warm from the sunlight. That's because it is absorbing the energy from the sun. Okay, so that's the second thing that can happen. Now, the third and the fourth thing are related. So reflection is when light strikes an object like a molecule of air and bounces off at the same angle that it came in. So an example of that would be looking in a mirror. So the light comes in and it goes back out at the same angle. That's called reflection. And if you think about it, that's clearly not absorption, because the light that's entering the mirror is not being absorbed, it's exiting. And it's not transmission either, because it's not going through. All right, and the fourth thing is called scattering. And scattering is exactly the same as reflection, but with one difference. And that is that when light strikes an object like an air molecule, if it is scattered, then it bounces off just like reflection, except it bounces off at a random angle. So a couple examples of scattering that you might be familiar with is when light shines on a disco ball in a nightclub. I'm sure you all frequent disco nightclubs. But light shines on the disco ball and it quote unquote reflects in random directions, all directions. That's called scattering. Another example of scattering is something that fascinated me when I was a kid. Um, I used to go to my grandparents' house, and they had a sofa that we kids were not allowed to sit on. So of course I was fascinated by it. I was trying to sit on it and getting in trouble for doing so. But if it was a sunny day, the sofa was right against the wall underneath the window. I could, with my hand, whack the sofa, and it would send up some dust, and I would see sunbeams in the dust. So that is an example of scattering, because the light from coming through the window was striking the tiny objects, the little pieces of dust, and they were scattering them. They were reflecting them in random directions, which is scattering, and that created the sunbeams. Okay, so now the first thing I want to talk about optics is colors. So visible light from the sun has all of the colors in it. So let's see. Light consists of a spectrum, which just means a range of wavelengths. So it's waves that travel from the sun, and the different sizes of waves are the different colors. And when we see many different sizes at one time, that's white. So actually, if you want to get technical, white isn't a color. White is all colors together. When you see only one specific wavelength, one specific type of wave that makes up visible light, then that's a specific color. Okay, so let's see here. Okay, here we go. So sometimes clouds are white and sometimes they're gray. So this is an aspect of atmospheric optics. It's less spectacular as some other things like rainbows, but don't worry, we'll get there. So one property of the water particles that make up clouds, and by water particles, I mean the tiny microscopic water droplets, or if it's cold, the tiny microscopic ice crystals that make up the clouds, is that they scatter all of the wavelengths of visible light equally. So that means that when you look at a cloud, you are seeing the light from the sun that the cloud scatters, and you'll see all of the colors together, and it appears white. So as the sun sends its energy towards the clouds scatter all the wavelengths of light, and scattering, remember, is reflection at a random direction. So one of those random directions is towards your eyes. So you will always see some light. Okay. Now, if you look at this diagram, it shows that more light is reaching the top of the cloud, of course, because the top of the cloud is directly facing the sun. So one thing that's interesting, if you ever looked out the window of an airplane and noticed that during the day, when the sun is out, the tops of clouds are always white, always. And that's because the particles that make up the clouds, the ice crystals and water droplets, they scatter all the wavelengths of light. Now, the bottoms of the clouds, which is what we earthlings can see, are sometimes white and sometimes they're gray. So gray is an interesting color, because whereas white is all colors together, black is the absence of color. And so gray is in between. So what's happening here is the top of this cloud is white, because the tops of clouds are always white during the day, that is. At night, they're black because there's no light at all. And they're gray because not enough light is penetrating to the base of the clouds to be scattered to your eyes. Okay. I teach meteorology classes in Mexico every year, and I usually give some of the fun presentations like clouds and optics and mirages and things like that. And my students frequently will send me photos and say, hey, can you put this in your presentation? So you're going to see a few like this. Okay, now let's talk about blue skies. Um, one of my early memories is as a little kid, I asked my dad, why is the sky blue? And you know, your dad, he's one of the smartest people you know when you're a little kid. And my dad very wisely told me that, well, the earth is mostly ocean, which is true. It's 70% ocean. He says the earth is mostly ocean. So when the sun shines on the earth, the light gets reflected off the blue oceans into the sky, and that's why the sky is blue. And I remember being proud that I had such a smart, wise father. And it wasn't until my first meteorology class in college that I realized that he was completely wrong. Um, Actually, what happens is that the molecules of air that make up our atmosphere, because of their size, they're very small, obviously, they selectively scatter the shortest wavelengths of visible light. And the shortest wavelengths are purple, violet, that is, and blue. So really, the color of the sky is violet and blue, but our eyes can't detect the violet. That's just a property of the human eye. We can see the blue, but we can't see the violet. So that's why the sky is blue. Now, sometimes the sky isn't blue, like when you have some pollution in it or uh, some water particles. So let me show you a few pictures here. So here in this picture, this is a picture of the, where are we? I think it's the Great Smoky Mountains, but I'm not sure. I don't remember. So if you look towards the top of the photo, you see blue sky. So what's happening is the sun is somewhere. I don't know where the sun is in this picture. Maybe it's behind the photographer, but the sun is shining on molecules in the atmosphere everywhere. And those molecules are scattering the light in all directions. One of those directions is towards your eye, but they're not scattering all the colors. They're scattering mostly blue. And that's why you see the blue sky. Now, closer to the ground, where you have the haze in this picture, the color looks more white. It's not exactly white, but it's whitish. It's less blue, more white. And that's because the haze particles, which are some combination of tiny liquid water droplets and air pollution, they scatter all of the colors. So that's the reason why you have these different colors. Haze scatters all of the wavelengths, whereas clear air scatters blue the best. So here's another picture. This one is the Smoky Mountains. And you can see that higher up in the photo where the sky is clearly blue, you can see farther. And closer down to the surface where the sky has this whitish tinge from the haze, you can't see as far because not only does the haze scatter all the wavelengths of light, but it also restricts the visibility. Okay. When you have more haze, the visibility is restricted even more. And you may remember this, that we had some regional air pollution events in the summer with the wildfires from Western Canada and also from Ontario. Remember that? That was in what, May, I think, May and June. And visibility was very poor for us on those days because of the haze that was accomplished by those smoke particles. Okay. In the Western United States, visibility is a big environmental problem because where you have these Western national parks, this one is Glacier National Park, shown in this picture. One of the biggest environmental resources of the parks is the scenic vistas. The tourists come and spend money in the local areas, in large part to see what can be seen. And so when you have pollution events, mostly from wildfires, that cause this haze that restricts the visibility, then that is a big problem. It's an economic problem as well as being an environmental and a public health problem. In the A, B, C, D panels here, you have the same vista shown, but different pollution levels. So in A, you have relatively little pollution, and in D, you have the most. So you can see that the pollution increases the haze, decreases the visibility. Okay. So next optical phenomenon that I want to talk about is crepuscular rays, more commonly called sunbeams. So crepuscular rays are really cool and they're really common. One of the things for me that makes an optical phenomenon really cool is when it is really common, because a lot of times you have to know when to look and where to look. And once you do, you're rewarded by seeing these beautiful displays of nature. So crepuscular rays. So here's an example. Crepuscular rays is a scattering phenomenon. So what's happening is that the sun is shining and the air contains some pollution particles. Now, the pollution particles, it might be man-made pollution like, stuff, emissions from factory smokestacks or automobiles, for example, or it could be natural contaminants like salt from sea spray or dust blown off of arid lands or something like that. But in any case, there are impurities in the air, and those impurities cause light to scatter. So what happens is as the sunlight is shining through the air, it's striking a particle that happens to be floating around in the air, and that particle is causing the light to reflect at a random angle, in other words, to be scattered, and that's what causes these beams of light that you see. Now, an interesting thing about sunbeams or crepuscular rays is that the individual beams that you see are parallel to each other. So here you have, well, let me go back. Notice that in these crepuscular rays, so this phenomenon that you see right here is called crepuscular rays. Notice that the rays appear to emanate from the sun. Okay, and so it looks like they're sort of fanning out as in the downward direction. Here you have the same phenomenon, but it's called anti-crepuscular rays. Now, if you think about it, if you look at a diagram like this, you're really looking at the same thing because the light is emanating from the sun. But in these photos, the sun is below the horizon. So it appears that the rays are fanning out upward. But in both cases, they're fanning out from the sun. Okay, and as I said, the interesting thing is these rays that you see are parallel. And I'll explain why in a second. This is another contributed photo from one of my Mexican students. Anti-crepuscular rays. Okay, so there is a very cool optical illusion that's called the convergence of parallel lines. So that is when because we have stereoscopic vision, meaning that, if both of your eyes work, when you look at something, you see it from two different angles simultaneously, one from your left eye, one from your right eye. And that creates an optical illusion, which is called convergence of parallel lines. So you can see it in the diagram to the right, you can see it in the photo to the left, where in both cases, the lines are parallel. And if you remember from your geometry class in school way back when, parallel lines never intersect. So it looks, and this is the optical illusion, it looks like they intersect, but they don't. So that's what you see, whoops, with the sunbeams, crepuscular rays, anti-crepuscular rays. The rays are all coming from the sun. They're all going in the same direction. They're parallel. But just like with the railroad tracks, at the top of the photo, it's very far away, and it appears that the lines converge. Well, the sun is even farther away, so it appears that the beams converge even though they don't. Okay, so let's go on. Next, I want to talk about rainbows. And I think you're lucky because I could talk about optics all day long, but rainbows can be my final phenomenon that I'm going to talk about this morning. Rainbows are probably the most spectacular optical phenomenon that you could ever see in the atmosphere. And coincidentally, they're one of the most common. So that is great. How often do things work out like that, where the very best thing is frequently available? So, all right, rainbows are a phenomenon involving the interaction of light with water droplets. Okay, not ice crystals, not pollution particles, water droplets. So it is a warm weather phenomenon. You rarely will be able to see a rainbow in the winter because in the winter you have fewer water droplets. It's more ice. And it is an entirely natural phenomenon, no involvement of pollution. So in order to see a rainbow, you have to be looking towards the rain. So you have to have rain, and the sun has to be at your back. So and furthermore, the elevation angle of the sun has to be less than 42 degrees. So exactly at sunrise, the elevation angle of the sun is 0 because the sun is just starting to come up over the horizon. Exactly at sunset, the elevation angle of the sun is similarly 0 because it's just dipping down over the horizon. In midday, depending on the time of the year, the elevation angle is fairly high. At the summer solstice here in Milwaukee, the elevation angle gets up to be around 80 degrees, like not quite directly overhead, but almost. And in the winter, the elevation angle is less. But you need, in order to see a rainbow, the sun has to be no higher in the sky than 42 degrees. And that's easy to figure out because straight up would be 90 degrees. The horizon would be 0. So 42 is almost exactly halfway. So, and also the sun has to be at your back. So if you follow the logic here, in the morning, when the sun is in the east, if you're going to see a rainbow, you have to be looking towards the west. Because in the morning, with the sun at your back, you'll be looking towards the west. And in the afternoon, if you want to see a rainbow, you will be looking at the east. So there's no way you can see a rainbow to the west in the afternoon. Okay, so rainbow is an optical phenomenon involving two physical things, reflection and refraction. So let me show you how that works. So when you have light, that's the yellow ray there, entering a raindrop, it has to reflect off the back of the raindrop. And that's easy. That happens all the time. So raindrops are liquid water. As you know, liquid water is partially transparent. So light gets transmitted through the surface of the raindrop and it reflects off the back and comes back out. So that's one thing that you need, and that's good because that happens naturally. Now, the other thing that needs to happen is you have to have refraction. Refraction is the splitting of light into its component colors. So remember I told you that light consists of a spectrum of waves, a range of different waves. And each individual different wave is a color. So up here, I don't know if you can see my mouse moving around, but up here you have the sunlight coming in, striking the raindrop, and the light splits into different components, different colors. Okay, and it's more than two. It's more like 8 or 9. But it splits. Each color gets reflected off the back of a raindrop and it goes out. Okay, and notice that each color goes out of the rainbow, I'm sorry, out of the raindrop at a slightly different angle. Okay, so that's what causes the prism effect in a rainbow, where you can see all of the different colors just like you can with the prism. Okay, and I'm going to show you some pretty pictures of rainbows in a minute, but some more background here. If light gets reflected more than once inside a raindrop, then you get more than one rainbow. So if light is reflected once, you get a single rainbow. That's called a primary. If it's reflected twice, you get a double rainbow. And actually, often light is reflected 3 and 4 and 5 times in a rainbow. In a raindrop. And when that happens, there literally actually are 3 and 4 and 5 different rainbows. The problem is that the light intensity of those additional rainbows is very small and our eyes can't see them. Okay, so here's a diagram of light being reflected twice. So you have sunlight coming in to a raindrop, it's refracted, it's reflected, then it comes out. So this is the scenario where you get a double rainbow. Okay, so here's some pictures. So notice that what's happening is you're standing here somewhere looking at the rainbow. Here's like the eyeball, that's supposed to be your eyeball. And the light is coming from the sun. The sun is, somewhere in the sky, less than 42 degrees elevation. And that is shining on zillions and zillions of raindrops. And many of those raindrops, this is happening, right? The light enters a raindrop, reflected once, reflected twice, and then exits with the refraction that causes the splitting of colors. Here's another. There are all kinds of interesting details about rainbows. Like, for example, you notice that the primary rainbow, this one, the one with the smaller radius, the inner one, notice that the red is on the outside, okay, and the blue green, blue, it's on the inside. But the secondary rainbow, it's the opposite. The red is on the inside, the green and blue is on the outside. So that's that reversal of the spectrum of colors is caused by the fact that when the sunlight reflects a second time in the raindrop, the angles switch. Okay, let's see. What else I want to talk about? Okay, so rainbows are a really easy thing to predict. If you have the sun shining brightly and the sun is at an elevation of less than 42 degrees, so that means that it's maybe within a couple hours of sunrise or within a couple hours of sunset. So you have to have the sun shining brightly. You have to have the sun at a relatively low elevation, and you have to have rain happening. So obviously rain can't be happening everywhere because then the sky would be covered with clouds and you wouldn't have the sun shining brightly. But if those conditions exist, and you've all seen those conditions before, you position yourself with your back to the sun and you're guaranteed to see a rainbow. So it's a great thing to do. You can predict rainbows. You can say, oh, conditions are right for a rainbow. I'm going to look, and then you'll always be rewarded. Okay, a couple more interesting things about rainbows. So another type of light is called infrared. So I don't want to get too deep into the rabbit hole of the physics of light here, but light consists of waves, electromagnetic waves from the sun that are of different types, and the different types are called wavelengths. So the kind of light that we could see, it's called visible light, has a certain wavelength range, but then the light that is slightly stronger, the waves that are slightly longer than that are called infrared waves. And this guy that I was telling you about, Robert Greenler, who was a physics professor at UWM for a long time, he had this brilliant idea back in the early 70s that said, hey, since infrared light is passing through the air all the time, that's another form of waves that comes from the sun. Since that's passing through the air all the time, just like visible light that we can see, shouldn't there be an infrared rainbow too? So he designed an experiment where he set up a hose in his backyard and created an artificial rainbow, and he filmed it with an infrared camera. Now, infrared cameras, they're the kinds of cameras that are used in night vision goggles. The military uses them. They're not that uncommon, really. And he took a picture. He took this picture that you see of an infrared rainbow. It's actually a double rainbow. You see one here, you see another one faintly here. And it was the first time in history that anyone ever observed an infrared rainbow. And that's really cool. That's sort of like walking on the moon, the first time that a human ever observed something. And he did it just because he had this idea that, well, shouldn't that exist? Brilliant. That's why he's my hero. Okay. Here's a more modern picture of a different experiment that somebody else did following Greenler's work. So in the black and white slices here, you see an infrared rainbow, and in the color slice in the middle, you see the normal visible rainbow simultaneously. So these are simultaneous photos, regular visible photos, and the infrared camera photos with the photographs spliced together to see this. It's very cool. Nice to know that there are infrared rainbows in the sky too, even though we can't normally see them. Okay, so I have one more thing to tell you. I already told you this. So let's go here. Here, this one. Uh, People say that there's a pot of gold at the end of a rainbow, but nobody's ever found it. So the reason that nobody's ever found it is because rainbows are complete circles. A rainbow forms a complete circle. And let's see, do I have a picture of this? Yes. So here you can see the shadow of the person taking the photo of the rainbow. And this is the head of the person taking the photo. That's called the anti-solar point. So it's where your shadow, the shadow that your head makes from the sun, where the shadow strikes the horizon right there, that's called the anti-solar point. And the anti-solar point is the center of the rainbow. Rainbow forms a complete circle with your anti-solar point as the center. So let's see. So sometimes you may notice that the rainbows form a nice deep arc like this. Well, the only way that can happen is when the sun behind you is at a very low elevation, maybe almost at the horizon. Other times, a rainbow will form a very small arc like this. Well, if that were to happen, your anti-solar point would be much farther back, and it indicates that the sun is much higher elevation. So you can, from seeing a photo like this, you can actually do a little bit of detective work, and you can deduce that the sun must be very low in the sky in order for person's anti-solar point to be almost up at the horizon. Okay, so rainbows form complete circles with half or more than half in some cases of the circle being underground. So that's why no one ever found the pot of gold at the end of the rainbow, because there is no end of a rainbow. Circles don't have ends. But if a rainbow is a circle, wouldn't it be cool to see the full circle of a rainbow? Well, if you think about the requirements for a rainbow, you have to have the sun at a 42-degree angle or less. You have to have the sun shining brightly in the sky, and you have to have rain. The only way that you could see the full circle of a rainbow is if you yourself were in the sky. And I actually did some Google sleuthing, and I found some photos that skydivers have taken when they were skydiving in conditions which were right. The sun was at their back and the sun was shining brightly and they were facing rain. And from that position, being in the sky, you can see the full circle of a rainbow. And in this case, in this photo, there's a double rainbow. Now I have, let's see, I think I have a video. I do. Let's see if this works. Yes. The skydiver is diving, something I would never do, but and someone's taken a video, but there you go. Now he looks down and he can see the rainbow. And because of the geometry of him being in the sky, he is able to see the full circle of the rainbow. I think that's really cool because he is able to see something that is there. We all know it's always there, but because of our position on the earth, we just can't see it. But all you have to do is jump out of an airplane to be able to see it. Okay, well, that's all I have for you today. So I'd be happy to take any questions if you like.